Hello. Hi, everybody. Thanks for coming to see me again. I appreciate that. So this talk is going to be completely different than the keynote I gave. That one was all about where we're going, what the future looks like. This one's all going to be about the nitty-gritty details. So probably for about half of it, maybe a little more, I'm just going to talk about our journey with Kubernetes. And then the second half, I really just want to answer any questions you guys have. Because for context, we deployed Kubernetes in our first cluster in our first production data center in October 2014, 0.11. I would not have recommended doing that necessarily, but it was a great learning experience, and we've been working very closely with the project along the way and contributing, and it's a totally different beast today, which is awesome. But over the last 2 years, we've now today have 4 clusters. 3 are in production, serving production traffic. All of them are on bare metal in our own data centers, and they're about 50 nodes each, with more being added every week now. And they're running several microservices that power box.com. So again, basically this talk is all about, you guys can just pick my brain, ask any questions you want. I'm going to just cover kind of at a high level what we do to enable our developers to use Kubernetes to deliver production microservices. And then, any of the things you guys have been running into trying to deploy Kubernetes, I'd love to either hear about or feel free to ask questions, things like that. So let's talk about what Box is for just a second. So we provide sharing and collaboration services for everyone from individuals to large businesses and governments all around the world. This is a screenshot of our product in the browser, but we also have applications on iOS and Android and Apple Watch and really anything you can imagine. And the idea is we make a very usable platform for the biggest enterprises in the world. So we have like General Electric on our platform, and they have over 300,000 employees using Box. And so you can imagine at that kind of scale, you need a lot of compliance and security and requirements and things like that we really specialize in. And so as of today, we're spending a lot of time thinking about how do we not only run stuff in our own data center, but also burst to public cloud. So that's why Kubernetes is really very relevant for us. So let's talk about how a developer begins their journey in launching a production microservice on Kubernetes. So first they start with their source code repo, and they have a Docker file in there. And then they use that, we use Jenkins to build a Docker image, and then we push that to Artifactory. So first let's talk about, which is what we use as our Docker registry. So first let's talk about the Docker file piece, because there's kind of like this dirty little secret about Docker files where Docker files expect that the image that you build your software in is the same one that you are going to run your software in. So if you imagine, like, you may want one image that has your JDK and another image that has your JRE, so that your run image doesn't have all the compilation or build tools that you may have. But that's generally not what Docker files expect. They expect one Docker file, you have the whole thing in there, you just throw in all the different tooling, and then that's the image you end up shipping. So we basically wrote a bunch of scripting and tooling that we haven't released yet, but if it reaches a critical mass, we will, where we have a Docker file build as an optional component that basically puts artifacts in a mounted location into the image, and then a Docker file that takes those artifacts and is able to copy them in. So you see the place that we put it is in the build directory, and so we copy in all those artifacts in to the runtime Docker file. So that's just one way that we worked around that. We go back and forth every day on whether this is really valuable or not. Like, maybe it is fine to just shove all your stuff inside of the base Docker image, because as you're making layers, you can then make a layer that only has your runtime stuff, so you're shipping kind of a lightweight piece. But there's like potential security concerns and things of having all your build tooling in all your production environments. So it's just something to think about. We looked all over. If anybody knows of any tooling that handles this for you or makes this easy, we couldn't find anything. The source to image stuff that Red Hat has released with OpenShift is pretty interesting, but it doesn't seem to do this either. So we're still wondering whether it's really worth the cognitive overhead versus just using a Docker file, but it's just something to think about, especially if you're in a high security or highly sensitive environment. Then the other thing I had up there was Artifactory. So why did we use Artifactory instead of the enterprise Docker registry or the CoreOS registry or any of those things? And it's because binary hosting is not a new thing. I mean, we've had the need for hosting of anything from jars to gems to RPMs to whatever it is for a very long time, and there's a pretty sensible feature set that gets built around that, whether it's redundancy or HA across regions or really sophisticated APIs to query your registry or query your binary repository. And Artifactory had all those things, and it just added something that made it compatible with the registry, and we're like, well, this is a really full-featured solution. We'll just go with that instead of waiting for all the other registries to catch up to that feature set. So we would recommend just choosing someone who's done this before. I know we actually were using Sonatype Nexus as our binary repository before, but they took too long to add Docker registry support, so we just switched over to Artifactory. And so the APIs and the extensibility of the registry lend a lot of really interesting and creative tooling. So like the tooling I talked about, we really want all your components to be able to be very programmable against, because the future we should be in is one where a new, like let's say Heartbleed or something like that releases. We should be in a world where completely automatically all your Docker images rebuild, and then Kubernetes basically does a rolling upgrade of all of your software, just alerting you if something goes wrong or if one of the nodes, pods or whatever doesn't come up. So like if you imagine that kind of world where literally you push a button and everything just kicks off, updates, the image building basically pulls down the latest packages, including the latest patched OpenSSL, rebuilds all the images, automatically kicks off all the CI to rebuild all the images, kicks off any kind of either imperative commands or updates your declarative config to point at the new images, and then deployment objects or whatever you're using in Kubernetes will just roll that out automatically. That's the world we should be in, and instead of manually updating these things and manually doing deployments. So that programmability for every major component of your infrastructure, and I would call a registry a pretty significant component, should be a high priority. And that's kind of proven by one of the products Artifactory is releasing now called X-Ray, which is really, really cool. It basically shows you all your artifacts and how they all relate to each other and what things contain what. So let's say you published a jar and then you publish a Docker image. Well, you can actually say, well, these are all the Docker images that still have that jar. And if you imagine an integration that you could build between Kubernetes and Artifactory, or really any Docker registry, to a certain extent, then you could actually have it say in real time, right now, on all my clusters and all my data centers, again, regardless of cloud provider, which instances of my app are running an old version of whatever package it is that I'm trying to update. So that's a really exciting thing about what X-Ray is basically scanning everything all the time. It's not basing it off of manual metadata. It's actually going in and scanning your Docker images and your packages and coming up with what's in each one and creating all those relationships in a graph inside your binary repository. So we're really excited about that. It's in still pretty early stages. It only works with a few package types, but they're building it out more. We'd love for that to be open, and I think there are some projects and initiatives on that front, but X-Ray is the one we're looking at now. And then finally, secure cloud hosting. Like, we really didn't want to deal with binary hosting, so we have them run it for us. And it's really cool. They have a lot of tiers. If you pay enough money, you can basically have them run it in your own AWS account. So you can really be confident about a lot of the security. So that's Artifactory. So as we talked about, we had our source code that had a Docker file and potentially Docker file build. Builds your Docker image in Jenkins, but just clicking a button. And some of them, if you git push, then automatically builds the image for you and pushes that to Artifactory. Another quick thing about some of the scripting we wrote here, Docker has a lot of command line parameters you can give for building, but what's really important to us, I think I have that back here. What's really important to us is, like, I can just write the Docker file and run a command, and the image just builds correctly and gets shipped to the right registry, named the right thing without me doing anything, right? That's the kind of workflow you'd want to build for your developers. You don't want them to like futz around with the different Docker build commands and the Docker push, and do I tag it correctly, did I name it correctly? Because if it's not standardized, then how's my build tooling down the line going to be able to find those images to automatically deploy them in a potentially like continuous deployment type flow? So we use these labels in the Docker file as metadata, and you're able to query those later. So it's a bit of a hack, but it works really well to prevent needing like another config file inside your repo to describe what the image should be named, or to describe different parameters you want to give the image, like what tag you should explicitly do. So we have like an automated system for just generating tags based on the Git hash and things like that. So that was another thing I wanted to mention. So we've got our image in Artifactory. Good, we got the first part done. We got our image. So how do we run our image? Well, we have to write our Kubernetes specs. And so these specs basically explain how to run the image that we just built. So for example, it has, well, I'll show the example in a second. But basically it explains all the ways of, all the parameters of how you might want to run your app, including command and environment variables and command line parameters or things like that. And we'll look at one in a second. But what's key here is that we have templating. So we have a centralized repository that we publish all these things to. And there's templating that helps people reuse different parts of their configs or pods or things. Because we all know pods are an atomic collection of containers that are atomically deployed and represent kind of an instance of your application. But what's tricky is actually being able to provide reusable components that people can build their pods out of. And you also want a template so that you can issue slightly different specs to the different clusters as necessary. For example, if you have the non-production cluster and then you have the production clusters, or you have different environments that you want to publish to, dev, staging, prod, and so on, you don't want to have text files that have the entire YAML or JSON written out every time, because that gets very, very manual to make sure that all the environments are running the same thing. So what we do is we use templating, and we use this specific library called JSONit, which is another Google project. And JSON is essentially a templating language for JSON. And what's great about that is that it produces JSON, it doesn't produce text. So you can use things like Mustache or your favorite templating language or whatever it is. But the big problem with those is that they produce text instead of producing JSON. So they have no idea if your JSON or whatever you're outputting is malformed or is syntactically invalid or things like that. But JSON, it will only compile and produce syntactically valid JSON, which is really, really nice. So this is an example JSONit file for our Hello World app pulled directly from our repo. And at the top you can see, so something really important here, you're gonna have a temptation when you first start with templating to make a full abstraction of everything below. Of all the Kubernetes core objects, like deployment services, secrets, config maps. You're going to want to make your own like box deployment or box service or your company name config map or whatever it is. And I think the jury's still out, but we tried that first and we quickly rolled it back and we undid all our configs and made them look much more like the native objects, because the native objects are that complex and configurable for a reason. It's because many of your developers may want to tweak different things. And the problem is that while 90% of all the specs will look the same at any given time, the 10% that's different will likely be different between each team and engineer. So we started with like simple box service or whatever, and we ended up adding, well, okay, a parameter for resource utilization customization, or a parameter for the restart policy, or whatever it is. And we added so many parameters that it was just like, we're literally maintaining a full copy of the Kubernetes API for no real gain. Because now it's two things you have to learn, and if a developer is trying to learn how to deploy a service to Kubernetes, it's a lot harder for them to go use Stack Overflow or the documentation or all these advantages you get from using an open platform. So we kind of bite the learning curve and we say, okay, fine, people are going to have to learn these core Kubernetes objects, because honestly, they're pretty good and they're pretty well designed. So we have the general structure of these all look like the Kubernetes objects. So there isn't that much abstraction between the developer and Kubernetes. So you got kind, deployment, and then you have a spec. We have all the other fields. I've kind of taken a lot of them out. But now the spec field, you have replicas 3. So if for those who don't know, a deployment object is essentially the way to tell Kubernetes, run n instances of my application, but if I ever change anything about the spec, do a rolling upgrade. So that's different than like a replica set or replication controller where if you change it, you have to actually go kill each one manually and then it'll respawn as a new one. Deployment object is a rolling upgrade for you. So that's been really great to do. And it really helps with declarative configuration, as you'll see. So here we have 3 replicas. We have the template, and in the containers section, you'll see that under image, we start to diverge from JSON, and we actually call a function that's in a library file in this templating repository. So we have this library that we have, this like templating library called image, and that has a URL function which will generate the URL for the image. And it takes the application name, and then it lets you switch on which environment you're generating a spec for. So we essentially have a make file that iterates over these templates once per environment. And those environments get mapped to clusters, basically. So this switch allows you to generate a slightly different JSON for each cluster while all the other pieces stay the same. So then you see command. That's going to be the same across everything. So we don't have to change that. And then you see ports. This is like the normal parts of the deployment object. You see environment variables, and you see resources. You can control how many resources you have. And what's cool is like this is it. Like if you take this, and then you also take the service object and the config map and secret, which look kind of similar to this, with whatever helpers that we may have added. You have the full description of your application, which again is incredible. It's like you don't have to go futz with the EC2 like ELB config, but then locally you have your HA proxies that you have set up. Like this is now what we have developers code to, and they're done. We, as a kind of DevOps operations team, we take care of all the rest. And this is kind of the layer that DevOps is really needed to flourish in the way that it was originally intended. And one other really cool thing you'll notice here is appconfd.container. So appconfd is our internal, appconf is our internal configuration delivery tool, which is now legacy because we'll probably switch eventually to config maps. But it's our internal tool that runs as a sidecar container. And because of this, I can actually basically refactor out that definition and allow people to use it like a library. So now your microservice, the pod, can be composed of a bunch of other binaries that are developed by different parts of your team. And this is so much better than doing it in the traditional ways through Puppet and installing them directly onto the VM or bare metal machine or whatever, because these teams can independently produce applications that, because of the Docker image, are entirely contained. So if my Hello World app uses, let's say, Python 3.4, and the appconfd container uses Python 2.7, then both of those can coexist very happily in a single pod. And that's really awesome, and I think it's going to really change the way we think about how we build things. We don't have to build as many client-side libraries because we can actually now build just binaries that share the same network interface and potentially share file system volumes as well. And we can build applications out of composing binaries together because of the power of Docker and containers and pods and things like that. So this is the template. And these templates up top, so we looked at that deployment.libsonnet one right there. Let me see that. Yeah, great. Kind of. You have that deployment.libsonnet, and that was the one we just looked at. And then we have all these other supporting template files. And that make file goes through and generates this app.jsonet, which includes all these other ones. So this app.jsonet will be generated once for every environment that we have. So this repo is containing all these files. Apps and release are 2 of the main subdirectories inside that repo. Apps is where all your JSONet files go. And libsonnet is just the extension for one that's included as a library versus one that's directly generated. And then you have, in the release directory, you actually have the generated JSONs. And we actually check them in. You don't have to, and we started out not doing it. But the reason we check them in is because it's really, really nice, especially for us coming from a Puppet background, to be able to have a full sense in the code review of the templating changes of what's going to happen to all your clusters. So you may change some parameter in deployment.libs on it, and you may expect it to only affect your local cluster, but then when you generate them and you put it in the code review, everyone can review that you're not accidentally changing prod. Not only humans, but also automated tools as well. So that's a really nice thing that we found is that actually generating these final versions and checking them in and being able to code review those along with the templating changes gives a lot of comfort and security as you're potentially making really big changes to your templates and how things are generated. So just to be clear here on this green, we have the first one here is our cluster. And the second one, the second path element here is the environment. So we have a local cluster, which we always call your laptop. We have DSV31, which for us is our non-production cluster. And we have production clusters 1, 2, and 3, which are in 3 different data centers. And you'll notice that the environment is kind of a variable that can change independently from the cluster. So we kind of want as few clusters, like Kubernetes installations, as possible, because then you get maximum utilization across your fleet. And so like you'll notice our non-production cluster hosts 2 environments, dev and staging. So that's a logical environment for the services running there. But our production cluster will actually run 3 different clusters will all run the same logical environment, being prod. So that's like an interesting split that you probably want to make. We've been going back and forth. We may start doing cluster per environment just to simplify a lot of stuff, but this gives us much better utilization. So we'll probably keep going down the track of one cluster can hold many different environments. And it's really mostly for compliance at this point that we don't just run everything co-located. We'd love to get there if we can have sophisticated enough security and networking controls. So next, we have that centralized Git repository that we talked about that had all those files in it, the templates and the generated JSON that describes 100% of what the infrastructure is. And we use that declaratively and then apply it to our many clusters, our 4 clusters. So this applier originally started life as nothing more than a bash script that looped and ran kubectl apply on all the files, the JSON files, inside the Git repository. So we don't use those templates files anymore. Once we generate them, we go ahead and use the JSONs because the JSON is the only thing the kube cluster would understand. So we use applier to basically iterate over and apply each of these. And apply, basically what it does, it's kind of like put. It puts the new version, but it intelligently basically deletes fields that may have been removed. So, and it allows you to merge your config with other systems that may be modifying those objects. So I could go more in depth, but but if you're interested, you can go check out some of the issues around it. It's a very interesting piece of software. We helped contribute a lot of the original code for how it reconciles changes. And so recommend checking it out if you're interested, but suffice to say for the purposes of this talk, it synchronizes the state of the Git repository with the state of all the production clusters. And because of Kubernetes' desired state, current state model with spec and status, you can do that. You can basically tell Kubernetes, this is what I want, and Kubernetes will take care of it, and then Kubernetes will report back to you in a different way what's actually happening in your cluster. So because of that, we can manage our config declaratively, which is awesome. So next, let's look at what those clusters look like in production. So remember the applier. We've gotten that in the top left, and that goes over that HTTP API. That's that known stable API, which is an amazing thing to program to because it doesn't matter where this architecture is running, where your Kubernetes cluster is. You always just hit that same API, and we're going to always have one repo that in a single way expresses how all of our microservices run regardless of the cloud infrastructure. And it's now the job of another team to implement that and make sure all the Kubernetes clusters are operating properly in all the different places. So we have that applier hitting the API server. So here you'll see in the lower left we have 3 bare metal nodes per cluster dedicated to etcd. And that's been a great experience so far. Anytime we've had issues, it's for an expected reason where we accidentally had one node down. This was before production, fortunately, but and then the one node was actually down out of the 3 for like a month before somebody noticed. And then we only noticed because the second node went down. And then etcd was like, okay, I can't do anything now. So then we brought both back up. So the stability and reliability we've been happy with. We haven't seen any issues that have been able to be pinned on etcd. So that's etcd. We put them on dedicated nodes. You don't have to, but we do just to keep things simple and keep ourselves a little sane. I imagine as all this stuff matures, this stuff will become more and more co-located and more flexible with where it exists. So we have dedicated etcd nodes. And we install the etcd RPM with Puppet, basically. But you could do it any way. You could spawn an AMI. Any way you wanted to do config management, you can still do that. But we're going to move to having those be managed with a container under kubelet. And then, so under the first two nodes you see here, those are our master nodes. So again, you don't have to dedicate nodes to these functionalities, but again, for simplicity and as this project matures, it can help. So we have two master nodes, and those do run API Server, Controller Manager, and Scheduler as containers under the kubelet. And the way we run those containers is we use Puppet to drop YAML files on disk, and kubelet is able to not only listen for API Server for how to run things, but it can also listen to files on disk for how to run things. So, or what containers to run, rather. So kubelet sees some files on disk, and it picks those up, and it runs those three containers. And what's cool is as soon as those containers run, the kubelet also knows that it should also try and find an API server, and it finds the API server basically it just spawned. And so in the API server, you actually are able to do kubectl like get pods and all the other management functionalities of Kubernetes on these static pods themselves. So basically, like, it's the whole thing of like when you start running software this way under Kubernetes, you don't want to run it any other way because you get so much functionality with being able to introspect into your infrastructure and exec and logs and all these amazing tools that come with Kubernetes and kubectl that you want to kind of run everything as much under it as possible. So while we could run these other components as RPMs and have it be separate, the more we can have under Kubernetes, the better it can be. CoreOS is doing some really, really amazing work with self-hosting and pushing the front and really being on the cutting edge of that. And we're really excited to see where that goes. So those are our master nodes that run those three main master components of Kubernetes. And then we have, n bare metal nodes. So we've got 4 here, but imagine 50 or 100 or however many. And that runs all of our different components. So I'm going to talk about a couple more high-level topics, and then I'll open for any questions or anything you guys have thoughts on what I talked about so far. So one thing I'll talk about is ingress. Ingress on public cloud is mostly a solved problem. They do it through ELB or GCP load balancer and node ports. I won't go too into depth on that. You can just look up the documentation on that. But ingress on bare metal is a very actively evolving thing, and we had to basically solve this before the ingress objects kind of took off. So what we did was we got the service load balancer. So imagine this is a dedicated node, another dedicated hardware node, and we took the service load balancer code from the contrib repository, which is still up there, which is responsible for listening to the API server for pods that match a certain service, and then it generates an HA proxy that maps basically DNS names to those pods, and then it bounces HA proxy. And then HA proxy listens on an anycasted IP on the host interface. So we now have the ability to stamp out multiple of these and have a highly available, horizontally scalable ingress tier. Because what happens is the DNS name is patterned off of our namespace and name of the service and the cluster that it's in. So like hello world dev dot the cluster name dsv31 dot box.net. So that DNS name wildcards to this anycasted IP, and then this anycasted IP is able to pick up the traffic and load balance it onto the pods. So that's basically how we do ingress for other services inside of Box being able to contact and enter into services into Kubernetes. And then for the Kubernetes service discovery internally from kube to kube services, we just do that with the kube proxy. So that's basically, Octoproxy is just our internal name for that fork we did, but anybody can use this, and I think the ingress projects are going to be very interesting and take the place of this. And then for networking, which someone always asks about, basically we're using Flannel. And if you don't know why people end up using things like Flannel or Calico for routing, it's because most networks are designed in a way where if you have a server, you generally are going to allocate one IP to that server. That's how most networks are designed, especially bare metal or even potentially private cloud networks. Is one server will essentially get one IP, and it's not designed. But on the flip side, Kubernetes networking architecture asks that each container running on a node gets its own IP. And so when you tell that to the networking guys, they just start laughing. And you're just like, no, but really we need it. And they just keep laughing. And then you're like, okay, well, now what do we do? So if you want to solve it on your own without the help of the networking guys, what you do is you run Flannel, which basically creates this virtual overlay that pretends for any given pod that has an IP, it can route it to another pod that has another virtual IP, basically. So, and that mapping to the underlay network is done automatically by Flannel. So you can have this kind of mesh that lives on top of your underlay network. The downside is those IPs are not accessible outside the cluster if you're not running Flannel on an external node. So and the other complication is that it's just more infrastructure that you have to worry about. And it has a small performance penalty both on performance and bandwidth. So because you're basically wrapping the packets. So we use Flannel today because that was by far the most expedient thing, and it's been pretty stable. It's every time we have an issue, we think, oh, it's probably Flannel, and then it ends up not being. So it's pretty stable. But we'd like to move to Calico BGP routing, which solves the same problem in a different way. And then once we do that, we're also right now looking at Calico ACLs to be able to isolate these pods from each other from a networking perspective. So we're really excited about that. So I think that's mostly it for networking. Yeah. Okay. So that's pretty much what we're doing. I'm going to take questions now. Another technology we're looking at that we think is really interesting is Linkerd for the service discovery piece. And so that would be backed by the Kubernetes API server. So it's not an entire service discovery platform in the way we'd use it, but it would enable us to have a lot more intelligence about how these different components are communicating to each other. So yeah, great. Okay, questions?
Yeah, so if you want to make an application configuration change, does that involve rebuilding your containers, or do you have some tool to be able to do that within your platform?
Yeah, so the question is, if I want to make an application configuration change, do I have tools to do that without rebuilding the image, or does it require rebuilding the image and deploying that out? So configuration is a super interesting thing that has a lot of different options and ways you can look at it. So the first configuration you can start with is really try and put as much in the image as possible, because as much configuration as you can put in the image that doesn't vary per environment persistently. And what I mean by that is you can do a rolling upgrade of it per environment, but you don't want it to, once you've changed it, you want it to eventually be consistent across all of them. For those, I recommend putting it in your image because it gives you the most power for rolling forward and rolling back. It gives you a really nice model. You put it in the image, you rebuild it, and now you do a proper deployment with all the tools that help you do deployments and the risk that comes with a configuration change. Your next option is basically dynamic configuration, which is the config maps. So we are using those. We like them a lot. We like that we don't need a separate infrastructure for configuration anymore. It's just built right into Kubernetes. The challenge with config maps, the challenge and the benefit is they change everywhere instantly as soon as you change the resource. So the way that we do that today is we just are really careful with them and we make them one cluster at a time. And we sometimes rely on the application to not be refreshing the state so we can do it gradually. Because again, config changes are just as dangerous as code changes in a lot of contexts. And you have to treat them as such. So so what we're most excited about is the best of both worlds, where they're looking at basically embedding config maps or creating relationships, I forget exactly how they're doing it, with the deployment object, so that's an atomic unit. There's a lot of interesting stuff there about how this API can evolve and becoming more atomic in its mutations and modifications, but that's one really interesting area where yeah, we would like the config maps to be able to be deployed just like an image change, but with less overhead because now we don't have to actually make an image change. So.
How about secrets? How are you handling those?
Yeah, question on secrets. So secrets in Kubernetes are interesting. On the one hand, they're great that they're database backed, they're secure as long as you secure to your API server and etcd, and they're programmatically access controlled, and because of RBAC and other access control, you can actually control which users and teams can access which secrets. The not so good thing is they're unencrypted in etcd, right? So that's the security team doesn't like that as much. So there's a couple ways we're dealing with it. One is we're looking at Vault. So we really like a lot of the Vault-backed integrations. Now, still in Kubernetes etcd, that leaves it unencrypted when it's being used, but we're trying to get our security team around the idea that they're protected enough. Even though they aren't encrypted, they're protected enough that it can be considered secure if it's locked down. And there's cool things you can do where if there's some controller that's responsible for managing the unencrypted secrets, at least programmatically, you could really lock it down so no human could even have access to the secret resources. Instead, it's controllers and automated systems that are pulling it from an encrypted source and putting it into the unencrypted format. So yes, it may still be unencrypted in etcd, but if you can lock it down enough where it's really, really hard to get access to them, then maybe that's acceptable. We're still working through that. Another interesting thing we're looking at, and we have an intern working on this right now, is, and this is one thing that's really cool about third-party resources. So imagine a third-party resource, or rather a Kubernetes object that lives in the Kubernetes etcd and is accessible by the API server, but whose definition is not owned by Kubernetes, but instead owned by a separate controller that you run in a pod yourself, okay? So that's what a third-party resource is. Really, really cool. And what we're looking at is creating a third-party resource called an encrypted secret that we make in Kubernetes itself, and then there's a behind-the-scenes controller that securely decrypts that into a secret that's only accessible to the services that need it. So that way we can check in our secrets to our source control, encrypted per cluster, and then automatically have them decrypted at the final leg. Which is really cool, and again, the more you can put your declarative config, the better. Right now, we have to imperatively create the secrets before we start managing our config declaratively, because we can't check in the unencrypted secrets, obviously, into the repo. So some of the stuff we're doing there. Yeah?
So two questions, if I could. One is, do you expect your developers to be always writing to native Docker, Kubernetes type specs, or have they expressed a desire for something like OpenShift? Have you looked at running, I mean, a lot of things you're doing with templating is kind of like what OpenShift does, and you could use Origin if you were worried about proprietary. So do you look into OpenShift, or your developers asking for OpenShift, or you would?
Yeah, so the question is around OpenShift and how a lot of the functionalities of OpenShift map pretty well onto things we've either wanted or had to build for ourselves. The thing is, you have to understand that like a lot of this has been in development over the past like year and a half, and the facilities we've seen in the various PaaSes that have been on top of Kubernetes, OpenShift, Deis, and those many of those, they're really amazing, and they do a lot of great stuff. But the amount of either constraints or coupling we would end up to with those platforms compared to the amount of value we would get for the specific use cases we had, the balance just wasn't there yet. In the future, I wouldn't be surprised if a year from now we're on OpenShift or Deis or one of these PaaSes, right? We're very interested in that space. We'd love to do less of this tooling on top ourselves. We would love to migrate to that. We just haven't seen something that's ready enough and provides enough for our specific use cases that justifies that extra abstraction layer and the complexity and kind of, to some extent, the restriction that comes with that. So we're following all the projects very closely, and we'd be happy to talk to all of them, and yeah.
The second question was, did you mention anything about tenancy? Do you expect to provide multi-tenancy, and how do you expect to do that?
Expectation around tenancy, multi-tenancy. Well, we do have all the different microservices running in the same clusters. So what we do for that is we just use Kubernetes namespaces, and that's been working pretty well. Yeah, so the question is, how are we doing Kubernetes upgrades, and are we open sourcing aux proxy in the applier? So on upgrades, we basically do the same thing GKE does, where we upgrade our master components first just by dropping new puppet configs, and then we go through one by one and we upgrade our minions just using an RPM upgrade, which is not what GKE does. They generate new VMs. But they do upgrade your master kind of for you behind the scenes. So upgrades have been pretty clean so far. We haven't seen any real issues. We did see an issue going from 1.2.0 directly to 1.3.8 because there was a bug there. But if you just upgrade to the latest 1.2x, then that works fine. So yeah, we upgrade the masters first and then upgrade all the nodes. And then for open sourcing Octoproxy, we think the shelf life is pretty short because of Ingress coming out, and also most of it's already open source and service load balancer. And so it's probably not worth the effort. But Applier, we are actively, I don't know, were you? Okay, you're bugging me on Twitter. Yeah, so we are actively open sourcing it. He's literally every single day, he's working on it. He's here somewhere. If you want, I can have you bug him directly. But the engineer working on that. So, but yes, it is coming, I swear to God. Yeah.
I'm curious if you can talk about the cycle of the developer. Let's say someone's working on a single microservice and they have dependencies on another one. What would be the life of the cycle for that developer for iterating on that and getting into the environment where you can put that microservices in
So the question is around what's the life cycle of the
development cycle, like iterations, like making a change, pushing that to the
Yeah, so it mostly goes through the flow of source code, commit your source code, push it, then once the new image is built, sometimes automatically, sometimes manually, you'll just bump the image inside of the image conditional, and then essentially roll that out cluster by cluster. We're trying to get it so we can generate a set of templates and then stage those cluster by cluster. And so we have something we're rolling out right now internally in the repo where we're able to make that distinction. But yeah, there's some complexity there. And yeah, like I said, we'd love to have this tooling be more broadly available. And we think that part of synchronizing your specs with the clusters, especially different ones, is probably one of the biggest areas of development and what we've had to do the most work for. Yeah.
Mentioned you had some issues around compliance or auditing or anything like that. Any best practices or making that faster?
Yeah. So the question around compliance and auditing. Currently, we're really excited about the Cube audit log, which I think was either released in 1.4 or is going to be released in 1.5, which has a proper audit log of all the actions. In the meantime, we use the authorization webhook to log every single thing going on, which was quite kludgy, but it worked. I think that area is new and nascent and needs a lot of work, and I'm really excited about the work that's been going on there. But yeah, essentially right now, we don't even have it yet integrated into our LDAP. So we are manually creating user accounts and then manually assigning those namespaces. But we're going to move. CoreOS has done a bunch of work on identity providers and integrating Cube with that. So we're going to move to that for single sign-on and LDAP. Compatibility, and then we're also going to move to RBAC from ABAC, which is the Red Hat contributed, or at least modeled after, authentication framework. Yeah.
Just to add, maybe I missed this, but are you doing any actually moving from underlying infrastructure, public, private, et cetera? Are you still running this on pretty much one set of servers in some kind of sandbox place?
Yeah, the question is where are we running clusters? So we have 3 production clusters in production data centers that we have, and we just right now are spinning up a production one in public cloud, specifically in AWS, and we're also looking at GCP and Azure and pretty much all the cloud providers. As a company, we want to become more diverse in the kinds of infrastructures we support, and so Kubernetes gives us the best path for that. Generally, yeah. I have about, I think I'm 5 minutes over, but I think I have 5 minutes until it's 11:50, so unless someone stops me, I'm just going to keep going. You guys can leave if you want. More than welcome to. I won't take offense, I promise. Go ahead. I'm sorry? Yeah, so logs and metrics, I think that's also pretty unsolved. For metrics, we use Wavefront, which we're pretty happy with, but unfortunately it's a commercial SaaS offering. It's not open source, but Wavefront we've been pretty happy with for metrics, and we just basically send data points directly to that. For logs, we use a combination of HDFS and Elasticsearch and as well Splunk. So, but the kubectl logs, the integration for logs and std out is really, really nice. So we use that for a lot of live debugging now. Yeah?
What are you doing for your databases?
We're doing nothing for our databases in terms of Kubernetes. We'd love to. We want to eventually move everything stateful into Kubernetes, but probably for the next year or two, we won't be looking at that. Our databases are all physical right now. Yeah. Yep.
Talk about security within the cluster, like do you run TLS between containers or things like that?
Yeah, so security within the cluster, we use mutual auth. It's basically our own home-rolled stuff. We just have each service do its own thing. We'd love to move to something like Linkerd would help with that, or some other projects. But for now, we just have mutual auth that we manage ourselves. So, okay, so I think I'll go ahead and wrap up now, but I'll be up here if you have any questions, so feel free to come up. Thank you very much.